Yeah, I think this is supposed to be pedagogical lecture or something, so I'm going to talk about I'd like to discuss some rather fundamental subject in condensed matter physics or many-body quantum submech. That is how quantum many-body system responds to U1 gauge field or electromagnetic field. And by studying this, we can introduce many concepts like polarization, and I also want to point out a rather surprising connection of this polarization to some other concepts in physics. So first I'd like to start from how we can define polarization and some subtleties regarding the definition of polarization, which is based on a recent paper by Haruki Watanabe and myself. And yeah, later probably I will also discuss some other papers. So the first issue is how to define polarization. So polarization is defined like this. So if you have some material, chunk of material, like this chalk or something, then in general this material can have some electric dipole moment. Which can be related to surface charge. This side has positive charge, this side has negative charge. Then this material would have some total electric dipole moment. But as you can easily see, if the surface charge density is constant, then total electric dipole moment is proportional to the area of this surface. And also dipole moment is also proportional to the distance between these two surfaces. So in many cases this is proportional to volume. And in real material actually the value of total electric dipole moment is depends very much on what you do on surface. But because in many cases dipole moment is proportional to volume, you can think there may be some intrinsic electric dipole moment of this system, which is proportional to volume. So you can define dipole moment per volume or something. So the dipole moment divided by the volume is called polarization or polarization density. And as I hope I can discuss, this polarization sometimes characterizes the nature of the system in the bulk. including topological insulator and so on. So it's sometimes useful to think about this kind of quantity. And so as I said, in reality, most material has boundaries or surface, and the surface charge basically determines this polarization. But if you try to compute this quantity using theoretically like a band calculation, then in band theory calculation, for example, you need to impose periodic band function. So if this polarization is some intrinsic quantity of some material, then we tend to think that or we want to somehow compute the value of this polarization based on band theory or something, then we need to define this quantity in periodic band function. And once you impose periodic band function, there is no surface charge. And in fact, it's not clear how we can define electric dipole moment or polarization. But there are many studies on this problem back in since 1970s or something. And people came up with some idea how to define and also actually calculate and characterize the system under periodic band function by defining polarization. So roughly speaking, this kind of study is called modern theory. And there are many papers. But one of the well-known results is definition of polarization for free electron system or band insulator. So for band insulator, you assume some periodic potential or something. And then following the standard textbook in solid state physics, you can start from Hamiltonian for single electrons, and then you can define Fourier transform. Then you can obtain effective Hamiltonian for single electron, which depends on momentum k. Then this momentum-dependent Hamiltonian has some eigenstates. Those are basically Bloch wave functions. Then you can solve the eigenequation for this effective Hamiltonian. And this is the Bloch wave function. Then what people back in maybe 70s or 80s found was that you can define polarization for band insulators using this Bloch wave function. So it's defined by integral in this momentum space. So for simplicity, let's assume here we are considering 1D system, although this can be easily generalized to higher dimensions. So the polarization is for this band insulator is given by some momentum integral of so this is Berry phase in momentum stable space, and this integral over R is like inner product. So after integrating over R, this is the well-known Berry phase in momentum space. And then you integrate over the Brillouin zone. Then you get some number. And if you are more familiar with field theory, this is something like Wilson line, the integral over the closed contour in Brillouin zone. And the earlier papers tell us that if you compute this for occupied bands, then you get polarization.
Sorry.
Yes.
A is a system size.
Sorry, this is the size of the unit cell.
Unit.
Yeah, sorry. So here I'm considering the 1D system. And, say this is a unit cell. So the size of the Brillouin zone is from 0 to 2 pi over y. Okay, so this is well-known formula, but one of the reasons we revisited this problem rather recently is that actually if you carefully think about this, it's rather subtle, and there has been some confusion, I think. So the reason is that so this procedure is pretty standard, but actually there are several ways to define this Fourier transform, or the several ways to define this momentum-dependent Hamiltonian. So that's related to different ways to define the Fourier transform. That is, so when you have, for example, the same thing can be said for lattice system or continuous system, but maybe to illustrate, I consider the electron system in the continuum when coordinate can change continuously. Then so Fourier transform is written like so sloppy about normalization factor, but so Fourier transform of the annihilation operator at location x is given like this. So annihilation operator at certain momentum times this factor e to ikx. And if you define Fourier transform in this way, then you can uniquely define the Hamiltonian, effective Hamiltonian by using this. And then you get some number for polarization using this formula. But actually for electrons or quantum many particle system in periodic lattice, this is not the only way to define Fourier transform. So another possible definition is that so this is again the same operator, annihilation operator of electron at location x, which can be expanded like this with some different operator. And now this Fourier transformation factor is defined rather by e to ik times chapter r, where this r is some representative portion of each unit cell. You can choose center or boundary or whatever, but let's say each unit cell is represented by the center of the unit cell. And then if your electron is within this unit cell, then R is this value. And if your electron is within this unit cell, then R is the location of this center as well. So of course, this X is related to R. So this is representative portion of unit cell, and this, in this case, the small r is a deviation of the location from this representative portion. So if x is here, then this deviation is small r. So of course, these two definitions are simply related by the phase factor of e to ik times r. So of course, these are not so essentially different, but just a different convention. And so actually,
it's not well defined for continuous system. I think it's for lattice system, so you can write by including another index for k.
mm-hmm.
Right? So if you have the two sides in your unit cell, then you can introduce a side to the k1 and a side to the k2. But anyways, you need some enough number of these corresponding to the number of sides.
Right, yeah, so actually,
the number,
yeah, okay,
that we speak, the number
yeah,
of x
yeah.
and the number of r are different.
right, yeah, so maybe I should add bounding index.
Masaki, one question. Isn't that just a gauge transformation? So you're choosing, and as you said, this is like Wilson loop, so
Yeah.
although the correct connection is gauge dependent, the Wilson loop is gauge.
Okay, so I will come to that point. So, yeah, actually, one of the confusion comes from that point. So this is Wilson loop.
Right.
So this is gauge, supposed to be gauge invariant quantity. But these two, as I will discuss in more detail, are actually related to different gauge choice.
Right.
So you might think this different choice of gauge shouldn't matter once you define the gauge invariant Wilson loop. But actually, it does. The reason is that the gauge is used in different contexts. So this quantity is gauge invariant in the sense of gauge transformation in this momentum space. So you can change UKR to some phase factor.
Right.
But so suddenly this Wilson loop is independent of this gauge transformation. But this difference is not the gauge transformation in this sense. I'm coming to that point later, but actually this difference corresponds to some different gauge. This difference does correspond to gauge transformation, but of a different type, not of this type. But this is related to rather gauge transformation in real space.
In real space.
Yeah. So I will come to that point. And yeah, so yeah, I need to include. I need to sum over bound index. But so the interesting point is that so this convention you might think natural. Okay, so I personally felt like this is more natural. This is maybe artificial. But if you study many literatures, in some fields, this convention looks like a more standard. Maybe. For example, in many papers on topological insulators, they use this convention. Yeah, actually, for some purpose, this is more natural. For some purpose, this is natural. But anyway, so these two are just a different Fourier transformation convention, which is simply related by this phase factor. But interesting point is that so you can do this construction and define this polarization using the Berry connection or Wilson loop in the momentum space. But what you find is that depending on which choice you make, actually the value of polarization is different.
Is it different by something different from the quantum of polarization, or because there is also this compact one, so
Oh yeah. So sorry, I forgot to mention that this quantity has is actually ambiguous in integer part by doing large gauge transformation.
So when you say it's different,
in fractional part.
In fractional.
Right. Yeah. So let's say this I denote P, and from this convention you get P tilde, let's say, and these two values are different. So that naively sounds like a contradictory to the statement that this is gauge invariant quantity. But as I said, the gauge invariance in this sense and these two different kind of gauge transformation in different sense. Okay, so I want to resolve why they are different and what does it mean. And interestingly, in order to answer that question, it's more transparent to go to many body formation. this also has been discussed in the past. So it's a bit similar to the situation with quantum Hall effect. So first there was this TKNN formula, which gave the Hall conductivity in integer quantum Hall system as a Chan number, which is given by a two-dimensional integral of Berry connection in the two-dimensional momentum space. But then later it was generalized to some many-body Chan number, which is related to the twisting boundary condition. And here the situation is similar. So the polarization is given by one-dimensional integral in the momentum space Wilson line for free fermion bound insulator. But that can be also generalized to many body system interacting electrons. And for this, we can impose periodic boundary condition to some many body system. And then with periodic boundary condition, the system can be regarded as a ring. And then we can put magnetic flux. Then, so the Hamiltonian, the many body Hamiltonian, now depends on this flux. Then for each value of flux through the ring, we can define ground state for this value of flux. Then this polarization as a integral in the Brillouin zone for free fermions can be generalized for this many body ground state, like so this is some many-body version of the Berry phase, which tracks the change of the ground state depending on this flux. And then, if you integrate flux from 0 to 2 pi, you get something like a Wilson loop in this flux space. And so this is the many body version of the polarization.
One question. So
Yeah.
typically the polarization per se is not a well-defined quantity.
Right.
It's only a change in the
Yeah,
polarization.
yeah.
Don't you need another integral, between an initial and a final state where you are computing the difference?
Yeah, so if you want to study, for example, how much charge is transferred and so on,
But
then
that is the only concept that is well defined, right? Because the polarization per se cannot be
yeah.
associated with
Yeah. Yes, indeed, this again has the integer ambiguity because of the large gauge transformation.
Right, but in addition, I don't think it is possible to assign a polarization in absolute terms to a state. I mean, like,
Yeah. But yes, yeah.
So it's only a difference that is well.
Yeah, I will come to
Okay.
that. But still, we want to define some formula for polarization, and for band insulator, I explained that depending on how you do Fourier transform, you get apparently different results. But as you say, polarization itself is not so physical. at least in this periodic boundary condition case.
Right.
Yeah. So, okay, so this is a many-body generalization of the polarization. But then you might think, okay, this looks like uniquely defined. Then why we had the two different results for boundary insulator, free electrons? Of course, if many-body polarization in many-body system is defined properly, it should be possible to compute this for boundary insulator. Then you should get polarization defined for boundary insulator. The resolution is that actually this formula is not quite unique, depending on how you represent this flux. So the reason is that I just said I insert the flux, but as you know, the particles living on this one-dimensional system, the ring, cannot feel this magnetic flux directly. But still, this flux has some influence on electron state on this ring. That is nothing but Aharonov-Bohm effect. But as you know, these particles are affected by this flux because you need some non-zero vector potential to represent this flux. And, the vector potential is non-zero around this region. That's how Aharonov-Bohm effect arises. But as you know, there is a gauge ambiguity in representing the same magnetic flux. So phi can be represented in different ways. So one natural choice is to take a uniform vector potential. So this vector potential in this ring along this x direction can be taken just as flux divided by the length of the system. And there are many other choices, many other gauge choices to represent the same flux. But another choice, for example, is to concentrate the vector potential at single point. Let's call it boundary. I can concentrate vector potential to, let's say, single point. And if you choose this boundary gauge, this is equivalent to imposing the twisted boundary condition. So, of course, these different gauge choices are equivalent, they are just related by gauge transformations. But still, depending on which gauge or some other gauge choice you make, this ground state wave function is different depending on the gauge choice. And if you calculate this integral, actually the result is different for this gauge and this gauge. So again, this produces, if you follow this calculation using this gauge, you get one value. And if you use boundary gauge or twisted boundary condition, if you follow the same calculation but using this gauge, you get some value. And, in general, these two are different.
When you use two different gauges, shouldn't you use the covariant derivative there when you put the derivative as a function of phi? Because that is essentially a derivative as a function of the vector potential. Right?
No, well, no. So as I said, so this A is the gauge connection vector potential in real space.
Yeah, yeah.
So if you want to take derivative by real space coordinate x, then you should add this connection, this vector potential.
Yeah.
But,
Yeah, the only thing I'm trying to say is, when you put in the first choice, and the way this derivative as a function of phi appears, is essentially is has to do with the derivative of the action as a function of the vector potential is the current, and the PDT is the current that is the gauge invariant, right? So somehow in both formulations, you should get the current.
I'm coming to that point. So both are picking up current, but in different ways.
Right. But I mean, current is covariant, right? I mean,
well, yeah, current is covariant, but these values are different.
Okay.
That's my point. And actually, so first I introduced this Wilson line momentum integral for the polarization in free electron systems, boundary insulator. And actually, if you apply this formulation to the special case of boundary insulator, then we recover the earlier definitions. So this in boundary insulator, this gives people, which was defined earlier using the Fourier transform using the real coordinate x e to I kx. And if you apply this to boundary insulator, then I get p tilde overflow. That is momentum space integral Wilson line using some particular conventional Fourier transformation using the representative position of unit cell. So the difference between these two definitions can be understood as a difference between the different gauge choice representing the same magnetic flux through the system. So then what this physically means is the problem. So as you said, polarization itself is not quite physical, but what is more physical is current. So for example, if the Hamiltonian depends on some parameter, some control parameter, besides the flux. So this flux is kind of artificial probe to extract this polarization and so on. But more generally, we are interested in pumping and so on. Then there is another control parameter, Hamiltonian, in which the Hamiltonian depends.
But actually, in this formulation, probably it's better to put the instead of a function of flux as a function of A, right? Because that is the right, like you know, in both cases A depends on the flux, but in one case
Right.
A is proportional to the flux, in the other case proportional to the delta function. And what I mean is, it should be true in both cases. If you instead of putting phi, you put A, and then you take
Yeah,
the functional
right, yeah.
derivative as a function of A in both cases, you will get the same result.
Yeah. So so yeah, more precisely we need to use vector potential.
Right.
But what we want to obtain is we are interested in is polarization as a function of some control parameter. And as you said, this polarization itself doesn't have much physical meaning. But for example, if lambda is varied very slowly as a function time, some adiabatic then the polarization changes as a function of lambda. Then dc and this change of the polarization is related to current. Because so if I briefly go back to the open band condition case, then change of polarization means that somehow surface charge must change, which means that the current must flow within the bulk. So for periodic band condition, we can no longer define a surface charge, but still when polarization changes, there must be current flow. And, so you can say that the polarization itself is not physical, but if you take derivative, then it should correspond to current, which is physical and in principle measurable. And then the question is, if the current is physical, then why we get two different versions of polarizations? So actually, in general, this version of polarization and this version of polarization, if you take a derivative, you still get a different result. But
You mean if in both cases you take the derivative as a function of phi?
yeah. But because in real space they have different dependence, you pick up different currents.
But what I mean is also phi in one case is the chemical, the vector potential.
Mhm.
In the other case, it's not, right? I mean, because you have this delta function.
Yeah, but you can still say that it's vector potential, but only at one point.
Right, but what I mean is, why not taking the derivative as a function of A, of the vector potential? So, in each case. instead of
Well,
taking-
yeah, so basically what I want to do is
Ah.
precisely like that. So actually, so I introduced two different versions of polarization, and I didn't discuss a control parameter, but for any control parameter, we can define P and P tilde in similar way. And if you take derivative, they are still different in general. But in this way, if we consider the derivative, then the difference between these two are more transparent, because so this one calculated using uniform gauge is related to the current, but because in uniform gauge the vector potential is changed uniformly everywhere, so this change is related to the current density at location x integrated over entire system. So this is like a current flowing in the system, average over entire system. On the other hand, if you take the boundary gauge, and calculate this P tilde, and if you take derivative, then you again find the current, but because in the boundary gauge, only the vector potential at specific point, that is x equals 0, changes. So this is basically given by the current density at x equals 0. So even though both measures are current, you are looking at a different quantity. And yeah, so our answer is that if you come to this point, the difference is quite natural, right?
Yeah, because the real current is the derivative of Hamiltonian as a function of the vector potential, right? So
pardon me?
The current is the derivative of the Hamiltonian as a function of the vector potential,
yeah,
the action, to be more
right,
precise. And in the second case, well, right, if you do the derivative as a function of the vector potential, then you will get the same current that you got up there, right? Because the vector potential, although it is 0, I mean, it can change over the whole chain. So I mean, right, the fact that the current is the derivative of the Hamiltonian as a function of the vector potential is always true.
Right, yeah, exactly, yeah. So this is just a consequence of current being derivative, yeah.
Right, and that is true in any gauge.
Right,
That's what
yeah. So
and it's always the same current.
Yeah. So of course, once we understand it's almost trivial, but still, yeah. But in the band insulator case, there are two different definitions of this Wilson loop, which is eventually related to these two differences. That's not so obvious at the beginning, I think. But so in this way, it's not surprising to have two different versions of polarization. Actually, you can also introduce infinite variety of polarization by choosing the different gauge. But also, now it's clear that this does not contradict with the gauge invariance of Wilson loop, because that gauge invariance is about gauge transformation in the momentum space, but this difference is about different gauge choice in the real space. So they are not contradictory. But yeah, actually we had the same question from the referee of the paper.
I got
that. Of course, I'm not implying that, but that's natural question. But yes, those are different type of
I swear that I'm not.
So I think that's hopefully clarifies the definition. And now I want to.
Is it easy to, generalize this kind of argument to non-uniform system, like a periodic system, with some finite period?
Yeah, so this can be applied to,
Even in that case, it is natural to take the uniform gauge, or in that case.
Yeah, so that's related to this Fourier transformation convention I discussed for band insulator. So for band insulator, I kind of assume the periodic potential, but still you can define the Fourier transformation using e to ikx. X is a real coordinate, which somehow corresponds to taking the uniform gauge, because this doesn't care where is unit cell, just distribute vector potential uniformly. That's in this band insulator theory, that corresponds to defining the Fourier transformation just using e to ikx. But once you have unit cell, you can care, okay, this is a unit cell, so let's use let's represent the position of electron using some representative position of unit cell. That amounts to choosing the special location in the unit cell. That's related to the gauge field concentrated on the boundary of the unit cell. So this applies to disorder system or non-uniform system. So hopefully this clarifies so maybe the message is, the polarization itself may not be physical, but there are multiple definitions. But the derivative of polarization should be physical current, but still which part of the current you look at, there can be different versions. Okay. Then I want to discuss a bit different issue, but also.
If you want to switch to a different issue, let me ask a question.
Yeah.
And I say that the real object in the universe has a finite dimension. Then the polarization is a well-defined quantity, I want to say. For a finite body.
For finite body?
System will have a well-defined polarization.
Well, you mean open band condition?
Yes.
Or, yeah.
And so we are usually interested in polarization for such a kind of system rather than a system with below the boundary condition. And for predicting a value for polarization for a body with open boundary conditions, do you have any ideas of which definition would give a more precise?
Okay, good question. So I think I briefly mentioned in the beginning, but
Well, first of all, that
Yeah.
polarization itself is not a well-defined quantity in some dynamic limit. That is another possibility, of course.
right. So yeah.
For example, you said that putting a gauge in the growth functions, the integral part is not well-defined.
Yeah.
But of course, for real systems, open boundary condition 1 and 2 are different.
Right. Yeah. Yes.
So I'm wondering that the polarization itself is a well-defined quantity in some dynamic limit or not.
So maybe I guess the brief answer is that it's not really well-defined quantity in some limit.
Suppose there's some ferroelectric with cubic shape and increase the system size. And
because
define that way, and let's choose another shape like sphere or and increase the system size. Some dynamic limit value are different depending on the shape of the body?
Or, well, I think it can be influenced by what is happening at the surface. So,
So,
really,
so
for some.
polarization is well defined, but the polarization density is not well defined in that sense.
Yeah, I guess it somehow depends on boundary condition in general. My guess, but I am not 100% sure. Yeah. Actually, as I mentioned, people use this quantity somehow to distinguish different ways. Okay, that's well,
But
that's
in
about
that
fractal
case,
part. Yeah.
The situation also the situation is also similar to a ferromagnetic system. I mean, the magnetization depends on the shape of magnet. So in real ferromagnet, there is a demagnetization field in the body.
But
The
that's
field
due
depends
to
on the
the
shape of the
due to the long range
yes.
dipolar force. So, wait, so this is not due to long range force. Yes. So
That is a basic. So it's a electromagnetic field is a long range.
well, yeah. Well, so I don't really have solid answer to your question, but my guess is that it's not really well defined in thermodynamic neurances. Maybe fractional part somehow, but yeah. Okay. So these are about different versions of polarization from these connections. But in the past, there are also other proposals on how to define the Berry phase, polarization. And there is one interesting proposal by Lester. So actually, he also contributed to development of this modern theory of polarization using the Berry phase and so on. But he later came up with alternative proposal. So that is to express the polarization using expectation value of some operator. And his idea is basically so polarization is related to the center of mass of electrons in electron system. So let's try to define the center of mass of electrons. So again, let's consider 1D electron system, but to make it well defined, let's consider 1D lattice, for example. Then if you have 1D lattice, then center of mass would be calculated by multiplying coordinate x to the number operator at site x. And I use sum over x, and then by divide by something, then you would get the center of mass of electron. That's basic idea. But this operator itself doesn't match with periodic boundary condition, apparently, because if you shift x to x plus L, then it's not invariant. So it doesn't seem to work with periodic boundary condition. So what Resta proposed was to make it somehow well defined for periodic boundary condition. It's introduced a related operator, which is defined by 2 pi I over L. L is the system size, system length in 1D. And then put this center of mass like operator here. And then this works with periodic boundary condition because if you change x by L, then you get the extra factor L here, but it cancels with this one. Then you get the difference is that 2 pi I times nx, summation of nx, but n is number operator, so it's always integer. And e to 2 pi I times integer is 1, so this operator doesn't change under this shift. So this is well defined. Then he proposed that we can consider the expectation value of u, which is in general complex number, let's say z. And then this is complex number, so this is decomposed into amplitude part and phase part. He proposed that this phase part reflects the center of mass of electron. So this phase part can be interpreted as a polarization.
But in either way, I would say that the imaginary part of U rather than the phase part would be more appropriate for polarization too. Because if you operate the space inversion symmetry, their part doesn't change sign, but the imaginary part changes sign because the sign.
Yeah.
So therefore it has the same symmetry as polarization with respect to parity operation.
Yeah, so
I say it is imaginary part of U would be more appropriate. Yeah, of course, as far as the PR is very small, they're equivalent. When PR becomes large, they are different.
yeah, so in this way, PR is only well-defined modulo 1. And so if there is an inversion symmetry, this must be real, which restricts PR to be 0, 0 or 1/2 modulo 1. Maybe it's the same thing as you.
But then the inversion, the phase goes to minus the phase, right?
Yeah.
So you are conjugating because x goes to minus x, so you get the conjugated. So it is correct. I mean,
The amples are different. Amples would be different. Of course, they are
So that depends on the wave function.
so you conjugate, right? And
Yeah,
then-
so often the inversion, spatial inversion transpose Z to Z conjugate, then PR must go to minus PR, but this PR is only defined modulo integer.
Yeah, but still,
Yeah.
it is true that P goes minus P drop modulo, whatever.
But the answer is that it's still different, right? The imaginary part U are different from PR defined in that way.
Sorry, I
Imaginary part U is Z modulo of Z times sine of PR.
imaginary part of Z is
Z modulo multiplied by sine of
yeah,
PR.
right, yeah,
So-
so 2 pi
so
of PR.
Is it that quantity is more appropriate for popularization?
I don't know. Well, maybe you can use imaginary part, but this is what proposed by Lester, and
Yeah, they have the same symmetry, which part
I don't know. What I'm going to say is that under certain condition we can show that this PR agrees with P defined earlier. In that sense, this is kind of natural definition. Maybe I don't fully understand.
I think there's a difference appears when the modulo of Z is very small.
Modulo, so you are concerned
Yeah,
when
yeah.
this one is very small?
Yes.
Okay, yeah, okay. So that's an important issue, but what happens is that in 1D insulator, actually this goes to 1 in the thermodynamic limit.
In any system?
No, so if you go to higher dimension, this generally vanishes, then this definition doesn't make sense.
Or I mean, for any system in 1D, even for any interaction system?
Yeah, for gapped system, we can see that this goes to 1.
But also, the polarization should preserve this homogeneous property that, if we rescale the volume of, you multiply x by lambda, right? Polarization should be lambda times polarization. And if you take the sign, that will not work. If
Yeah,
you take
but-
the sign of that function and the rescaling of the variables, you will not get lambda times space. You will lose the homogeneity of the Makes sense.
Maybe we can discuss it later. But yeah, so Sam's question is very important. So actually, this formulation makes sense when this absolute value of Z goes to 1. But in higher dimensions, generally this goes to 0. Then this doesn't make much sense. In 2D, maybe it still works, but so that's proposal by Lester, but then I can make several remarks. So one question is I already mentioned in the discussion, but how this definition, alternative definition, is related to other maybe more standard definition of polarization. So one thing is that for one-dimensional insulator, this alternative definition actually agrees with the earlier definition using the uniform gauge. So actually this equivalence, I think, has been discussed in paper by Lester and so on, but I think perhaps more complete proof was given in my recent paper with Haruki. But maybe it's also useful. I'm not going to give you the full derivation of proof. If you are interested, you can check our paper, but maybe I can briefly mention why they are equivalent, and also the relation of this definition to some other concepts appeared in physics. So actually, also in order to show this equivalence, it's useful to notice meaning of this operator. Actually, this operator, the Lester, I think, introduced this operator from this center of mass kind of argument, kind of heuristic. But actually, this operator has appeared in many other contexts in physics. That is, U is essentially the same as Lipschutz-Matisse twist operator, which appeared in the proof of Lipschutz-Matisse 61. And also this U is nothing but large gauge transformation operator. So perhaps you are aware of what maybe I will explain what large gauge transformation means. So again, we consider the 1D system as a ring and flux phi. Then, as I emphasized, that this flux is inside the ring, so particles on the ring cannot feel this magnetic flux directly. So classically, in classical mechanical sense, these particles shouldn't be affected by this flux. But if you go to quantum mechanics, then this flux influences the motion of the particle on the ring. Well, because if you change the flux in time-dependent way, you do induce electric field. But for static flux, in classical sense, these particles shouldn't be affected by static flux. But in quantum mechanics, through vector potential, this flux affects the motion of particles on the ring. That's nothing but Aharonov-Bohm effect. But the Aharonov-Bohm effect becomes absent when this flux is equal to so-called unit flux quantum, because this phi is basically the basically phi is the atom Born phase. That is, if electron travels this way or this way, you get the extra phase difference phi. So when phi is 2 pi, so that is, I think, in some more physical units, it's hc over e or something. Then the phase difference, atom Born phase becomes 2 pi, and the 2 pi phase difference is equivalent to 0. So for this special value, the AB effect is absent. Which means that the Hamiltonian with 2 pi flux and the Hamiltonian with 0 flux, they must be equivalent, and all the spectrum should be, for example, energy eigenvalues must be the same, identical. But because for phi equals to 2 pi, you have a vector potential, and so let's take uniform gauge. A is phi over L. Then this Hamiltonian has non-zero gauge potential, vector potential. This has 0 vector potential. So these two Hamiltonians are not the same, although they should have identical spectra. So this relation between these Hamiltonian is exactly given by this large gauge transformation. That is, precise relation is phi equals to 2 pi is given by, I'm not sure, U or U inverse. So if you apply this transformation U and U inverse to original Hamiltonian, then you get this, or vice versa. So in this way, the U is the large gauge transformation. So this also kind of gives a physical picture how the original definition of polarization P and Lester's definition PR are different, but still gives the same answer for 1D gap deturator. So the original Berry-Face type definition of polarization was given like this. Actually, there is more subtlety, but I don't discuss it here. So this is like a Berry-Face for flux insertion. But here I'm using ground state for given flux at each value of flux. So this corresponds to Berry-Face corresponding to adiabatic flux insertion. So you start from flux 0 and then gradually, slowly, very slowly increase the flux up to unit flux quantum. And after inserting unit flux quantum, your system basically comes back to the original state. Then the Berry-Face can be very defined. So this is corresponds to physically corresponds to the Berry phase when you change or insert the flux adiabatically very slowly from 0 to 2 pi. Then what is PR? That's another question. So we can actually consider the opposite limit to adiabatic insertion. That is sudden insertion of flux. So by sudden I mean the value phi, and for negative t we have 0 flux, and then at t equals 0 I just switch on the flux. And we assume that the system was in the ground state before t equals 0. So we can consider this kind of sudden switching of flux or vector potential. Then in this case, so this is kind of quantum quench, but we are interested in what kind of state we obtain after this switching on of the flux. So actually this is kind of standard situation we encounter in some quantum mechanics textbook. So actually it's not easy to consider what happens at large time, but at least just after the switching on. So Hamiltonian changes at t equals 0 from 0 flux to finite flux, but the change is finite. So in this kind of case, we can apply so-called sudden approximation. That is, the wave function cannot follow the change of the Hamiltonian. So just after switching the Hamiltonian to different Hamiltonian, the wave function remains the same, which means that the wave function just after switching on this vector potential must be still given by the ground state. And I said approximation, but this should be exact in this. So it means that the wave function doesn't change. But on the other hand, if you switch on the vector potential or flux, you should have induced electric field, which was delta function like. So physically, this electric field should accelerate particles. So this looks strange. But the resolution is that this phi equals 2 pi and the phi equals 0 were physically equivalent, but in a different gauge. So in order to compare the new state with the old state, we must go back to the original gauge. Then you can make comparison. So the wave function doesn't change, but you are in a different gauge, which means that in order to compare with original state, you do the large gauge translation. Which is given by u times cosine. So this is a wave function after inserting a 2 pi flux, but in the original gauge. Then, actually, the quantity rest are introduced to define the polarization can be interpreted as overlap between this new state with the original state. This is what Resta considered. So it was expectation value of u, but actually you interpret as amplitude between these. So if you compare these quantities, they are similar in the sense, but are different. So that is both are related to the kind of Berry phase for flux insertion. But in this definition, it's a Berry phase for adiabatic insertion, so very slow insertion of the flux. But this quantity is related to the basically same kind of phase, but for sudden insertion of flux. So of course there is no guarantee in general that these two are the same. But for 1D gapped insulator, we can show that they are indeed same. That means that if you have 1D system and has a gap, then even if you apply delta function pulse of electric field, the ground state remains almost like ground state. And this phase is identical to this one.
So, but isn't that guaranteed by the fact that the Berry phase is known to not depend on the adiabatic assumption? So I mean, although it was originally derived under asking for adiabatic conditions, I think the adiabaticity is not.
Yeah, but in more general case, actually, okay, so how to say? Yeah, for example, even in band insulators, if we go to 3-dimension and higher, we can show that this amplitude itself vanishes. Yeah. So maybe the phase part.
But the phase part can still be rescued, right? I mean, because what doesn't depend on the adiabaticity condition is the Berry phase, so it's only the phase. I mean,
Okay, so yeah, okay, so maybe there is some more general correspondence than what I know at the present, but yeah, okay, so this at least we can interpret this as a Berry phase for adiabatic flux insertion process,
Right.
but this may be more general.
But somehow what you are doing is generalizing this thing to a non-adiabatic process, right? And as far as I remember, I think
Okay,
the
yeah,
Berry phase.
maybe you're right. But what I know for present is that for 1D gapped insulator system, we can really show the equivalence of this.
So can you prove that there is no level crossing during the adiabatic flux insertion?
Well, okay, that's a different issue. So to prove this, we assume that this level crossing doesn't occur. Yeah. So we assume that the gap is always finite during the flux insertion process. That's the assumption we need to prove.
It's assumption.
Yeah. So in this way, we can see the similarity between these quantities, but maybe some difference. And another thing I want to mention, another thing is already left, but actually the quantity essentially identical to this Lester's polarization was also discussed in some other context, that is quantum spin chain. Or maybe this quantity PR was I thought which was earlier, but I guess around the same time independently by Nakamura-san and Todo-san. So if you have quantum spin chains, you can introduce some other term. And so on. Then you can relate this quantum spin system to many particle system. And I require my Hamiltonian to have U1 symmetry. Which corresponds to rotation of spins about z-axis. Then total SZ is constant. Then we can interpret this SZ as some particle number. Here, let's consider general spins. Then we can, for example, identify SZJ equals to minus S. That's a minimum possible value as a vacuum, zero particle. Then SZJ plus S, you can identify this particle number. Then this large gauge transformation operator. I have used X, but if I label each side by integer j, then J. So this was operator also used by Lester. But if you do this mapping, then in spin chain context, this can be replaced by times some phase factor, but this phase factor is constant, so I can use this. So actually this is what deep shoot mattis used in their original paper, deep shoot mattis theorem. But anyway, so for spin chains we can use this, and then we can consider expectation value of this operator U in the current state. In Lester terminology, this phase part is given by PR. The phase part defines the polarization.
I have a question.
Yeah.
This set. So there was also a question, but this absolute value of Z,
Mhm.
are you really sure that in a 1D initiator it's always 1? I thought that this was related to the localization things or something like
Mhm, mhm.
that.
Yeah. So I think it's E to maybe minus L over localization length or something. So I think in 1D insulator it goes to 1.
In the large
Sorry, so in some limit, yes. For finite size, yes, it's generally not equal to 1. But I was interested in some limit. And so well, Nakamura-san, Todo-san didn't mention polarization, but they were basically looking at the same object. And what we can also say is, we also already discussed, but in addition to this U1 symmetry, we can also require several other symmetries. And one of the possible symmetry is the spatial inversion symmetry. So spatial inversion sends J to minus J, modulo L or something. So which sends Z to Z star, which sends PR to minus PR. Yeah.
Isn't it also, so the percentage, shouldn't they go to 0 in the large L ring? And the
This?
yes. in the
Well, actually, this goes to 0 for gapless conductor. But
for insulator,
insulator, I think it goes to 1. Yeah, actually, so I think we proved that this quantity approaches to the Berry phase.
phase is okay.
Well, I mean the Berry phase integral. So, well, yeah, actually, yeah. For example, yeah, I'm actually going to discuss, for example, AKFT state in spin chain. For that, I think we can explicitly calculate this for finite size system. Yeah, maybe we can discuss it, but that's an important point. But I believe this goes to 1 in case of gapped insulator. Okay, so if we require spatial inversion symmetry, then well, if we apply spatial inversion, PR should go to minus PR. So if your ground state is invariant under spatial inversion, then PR must be minus PR, which looks like implying PR equals just 0, but PR is only defined modulo integer. So this spatial inversion actually allows not only 0, but also 1/2. And so 0, PR equals 0 applies to rather trivial kind of insulators in electron language. But the 1/2 one, if there is a ground state which has PR equals to 1/2, then it's more non-trivial. And actually, for example, if we consider spin one chain, and one trivial ground state is obtained by sending d equals to infinity. D is the coefficient of SZ squared in Hamiltonian. So if you have this term in the Hamiltonian and if you send d to infinity, then for spin one chain there are 3 possible states at each side. SZ equals to plus minus 1 or 0. But if you have this term with very large d, then SZ equals to plus 1 or minus 1 is penalized. So you are only left with SZ equals 0. Then we obtain so-called large d state. Or large d phase, which is given by every site is occupied by SZ equals 0. But because SZ is related to particle number in this way, so this SZ equals 0 means everywhere we have one particle. So in this case, okay, it's maybe not so trivial. So maybe
You have to use the second definition.
Yeah, this is better. Yeah, okay. So if we, okay, so maybe I shouldn't mention this. Okay, thank you. So if you use this definition, then every side S equals 0. So in this case, this expectation value of U is just 1, which means that this PR is 0. So this is an example of trivial phase which has PR equals 0. But Nakamura-san and Todo-san pointed out that actually there exists a non-trivial phase which has PR equals to 1/2. That is, we have, for spin 1, we have Holden phase, and the representative state of Holden phase is given by AKLT state. So the ground state of the standard Heisenberg chain with spin 1 is supposed to be in Holden phase. But the ground state is not exactly solvable, so there is a representative AKT state, which is ground state of some modified Hamiltonian, probably most of you are familiar with, which is represented by this kind of picture. So each dot represents spin 1/2, and this is a singlet pair of spin 1/2. And at each side you have two spin 1/2, and you symmetrize the wave function. Or projection to triplet sector, then you get some wave function for spin 1 chain. And this is AKT state. And I'm not going to show the detailed calculation, but because this is some exact wave function you can write down. So for this state, you can evaluate this expectation value, which was what Nakamura Todo did. And for very long chain, this approaches to -1 for this AKT state, which means that in terms of polarization defined by Lester, this corresponds to Pi equals to 1/2 state. So Nakamura and Todo proposed that this can be used as a kind of order parameter characterizing the Holden phase. Even though they didn't realize Lester was proposing very essentially the same thing, but they studied this in the spin chain context. But in terms of polarization, this corresponds to 1/2. So I guess maybe intuitive understanding is like in trivial state, like large D state, each side has exactly one particle. So the center of mass of these particles is located at some site, this side or this side. Of course, in periodic boundary condition, it's not possible to distinguish this side and this side. So you can say the center of mass is either here or there in the large D phase or trivial phase. Or large D phase is essentially what people call as atomic insulator in topological insulator business. So in atomic insulator, the center of mass is this side or this side. Doesn't matter which side you choose. This ambiguity is related to the ambiguity of polarization by any integer. But if you consider this AKT state, then the center of mass of this particle system is actually at the center point, roughly speaking. That may sound strange, but it's somehow consistent with this picture. And if you do calculate this quantity for AKT state, you do get -1, which implies the center of mass position is somewhere in between the point, in between the site. And from this, as long as we have U1 symmetry and inversion symmetry, this PR must be quantized to 0 and 1/2, as long as there is a gap. So, which means that you start from, let's say, AKT state with PR equals to 1/2, and change the Hamiltonian, add some perturbation to change the Hamiltonian. But as long as you keep inversion symmetry, and as long as there is a gap, then PR cannot move from one half. So you cannot adiabatically connect AKT state to trivial state like largely. So this, in modern terminology, implies that this AKT state belongs to so-called symmetry protected topological phase. In this case, this is nothing but so-called Holden phase. But the point is that this Holden phase for spin 1 chain is well defined as long as you keep some symmetry. That's, in modern terminology, it means that it's a symmetry protected topological phase. That is, as long as you keep the symmetry, you cannot adiabatically connect this Holden phase to trivial state because of this quantization.
How about the 2D AKT state?
Yes, 2D AKT state, if I remember correctly, it belongs to some so-called weak SPT phase, which is kind of SPT phase, but it requires translation symmetry to be well defined. Yeah, I mean, you mean AKT state on square lattice, for example.
Yeah, for example, yes.
Then if you cut, then you have edge state, which is like a spin 1 half chain. But if you break translation symmetry along this edge, then you can diagonalize this spin 1 half chain. So if you break the translation symmetry, it's not generally very
The
difficult.
AKT state, the AKT model on the torus, then I mean,
Well,
we can.
but I mean, the well-definedness of SPT phase in the bulk is related to the stability of edge state. They are not one-to-one, but I think I forgot how to prove, but I think that general consensus is that the 2D AKT state belongs to so-called weak SPT phase, which is kind of SPT phase, but it requires translation symmetry to be well defined.
And the OSPT is also characterized by the polarization.
Okay, that's different issue. That's actually I'm not sure. This works at least for 1D.
So does this PR equal to 1/2? Anything? So this PR equal to 1/2 for the AKLT state. Does it have anything to do with this double degeneracy or entanglement?
Okay, so I don't know how to relate this directly to that, but well, I think this PR equals 1/2 kind of implies that if you cut the system, there is some.
Okay.
But you will get the same value, right? You will get the singlet between the two spin and cut, and then the formula that you give at the beginning is 1/2 minus.
Yeah. Something like that. And also, for any AKT type state with odd number of valence bonds, we find PI equals 1/2. So yeah.
I have a question.
Yeah.
This result is also valid for the K-type for Marangfang chain?
Oh, K-type chain.
Certainly, there you don't have a U1 symmetry.
Right. Okay. So I don't know. So far I have assumed particle number conservation, so it may not directly apply to K-type chain.
Yeah.
But well, maybe we can define something similar. But I don't know. Yeah. At least so far what I discussed assumes the U1 symmetry particle number conservation. So I don't think this directly applies to K-type chain, but maybe some generalization. Okay, so I'm running out of time. So, but one thing I want to mention is that this concept of SPT phase was kind of established more than around 10 years ago by Guen and some of our papers. But according to Masaki, all those physicists' argument to establish SPT phase was not really rigorous in mathematical sense. And just recently, last year or something, Masaki came up with rigorous proof that SPT phase really exists. And his proof was actually based on this polarization formula, although he doesn't rely on physical concept of polarization, but his argument is that so he starts from AKLT model and also some trivial state. Then so in AKLT state, this expectation value was -1. In the trivial state, this goes to +1. And then you impose, let's say, inversion symmetry. Then, as Tsugu-san said, this expectation value must be always real. Of course, I'm just giving you a sketch of his argument. He does mathematically rigorous way, but essential point is that if you change the parameter and try to connect between these two, but if you impose inversion symmetry, it's always real, which means that between these 2 points, there must be some point where this expectation value should be vanished. And if this, okay, in general, for spin one chain, this doesn't vanish. But between these two limits, there must be a single point, at least one point where this vanishes. And then when this vanishes, what you can say is that actually you can consider the energy expectation value in this U psi 0 state. And if you go back to the original paper of Lipschutz-Mattis, then they show that this is some ground state energy plus some order of 1 over L. But this is valid for any spin chain with U1 symmetry. But Lipschutz-Mattis theorem only works for spin 1/2 or 3/2 and so on, or incommensurate system, because in general there is no guarantee that this U psi 0 is different from ground state. for spin 1/2 chain or spin 3/2 chain, psi 0 and U psi 0 are orthogonal. But for spin 1 chain, generally, the orthogonality doesn't work. But now, between these two limits, there must be one point where this overlap vanishes, which means that the U psi 0 is orthogonal to psi 0. So this directly implies that at this point, there must be gapless excitation. So that means that there must be critical point separating these 2 points, whatever path you choose, as long as you keep the inversion symmetry. That's a nutshell of Tasaki's proof. According to him, this is the first regular proof of the existence of ISSP. So, okay, so I ran out of time, so I stop here, but there are other maybe interesting application. That is, so far I have discussed only gapped system, insulator system, but we can also consider this kind of quantity for gapless phase. Then you do excite the system, so this amplitude generally goes to 0. But if you consider finite size system, you can ask how fast this amplitude goes to 0. And that maybe characterizes how good the system is, how good contact the system is. And we did find some interesting scaling, and Furuya-kun recently gave some nice field theory understanding how this scaling works. But I don't have time to discuss all this, but one further application is which is also related to what Oka-san was doing. So I hope I have introduced some apparently very basic fundamental concept, but if you look carefully, so this quantity is connected to many different concepts in physics, and maybe some interesting application. Thank you for your attention.
So it's not a question but a comment. As I said before, there is some example pairs where polarization should be defined. For example, if we consider the molecular crystal.
Okay.
So there's the naturally polarization density would exist. And I want to know that for such situations, which definition gives a more correct answer.
Okay. Yeah, good question. Maybe I have to check. Yeah. Thanks for comment.
Briefly, so to understand, so then, if I understand correctly, so one can have, many systems with U1 symmetry. We can couple them to a U1 gauge field. The polarization is the response to what would be the uniform electric field in that system. And then one can play the same game somehow in all of this. So one can compute the polarization through this very phase. The derivative of polarization is a current, that is the derivative. And somehow is that the message somehow that so one can somehow replicate this similar kind of argument in any U1 variant?
Yeah.
It's not related, but what should we expect when U1 symmetry is spontaneously broken?
That's a good question. Okay. Yeah.
Usually, I thought about it, but usually it's a conducting, right? It's a gapless.
Yeah, but still maybe it's relevant to this. So. Any other questions?
I also want to make a little comment, that is that before Nakamura, there is a group of people, Armando Aligia and Gerardo Ortiz, that they did these kind of things. Actually, they computed this very phase, 0 or pi, to characterize quantum phase transitions, and coming from the paper from REST.
Okay. Okay.
That is from the 90s.
I see. Okay. Thank you. Yeah, so I found many papers doing the same thing independently.
In the 90s, there was a lot of activity on
Yeah,
this, and actually it was noticed,
Yeah.
that using this concept of REST, one
Okay.
can, they were using this very phase to characterize phase transitions actually in one-dimensional systems with Langham's, computing the very phase and showing that you get 0 or pi.
Oh, and in that context, I also mentioned that some of you know series of papers by Hatsugai-san and company who introduced, I forgot the name, but some local Berry phase for local twist, which actually corresponds to this P tilde version of the polarization.